So now we will discuss some properties of the elements across the periodic table, such as the electron gain enthalpy, ionization enthalpy, and electronegativity and the atomic radius, right? So to understand all the variation in this property across the periodic table, first of all we need to understand the variation in the atomic size. So ये सारी प्रॉपर्टीज जो है डिपेंड करती है इनके इलेक्ट्रॉन कन्फिग्रेशन पे भी, राइट. For example, we have D block, P block and F block, and also there is S block. So now we are going to learn some of the physical properties such as the atomic radius, ionization enthalpy, electron gain enthalpy and the electronegativity. So all of these four properties can be explained with the help of just atomic radius only, right? In order to discuss all those properties, first of all we have to revise the concept of effective nuclear charge and screening constant that we have already learned in our previous lecture. Now we are going to discuss the atomic radius, right? So this it is defined as the distance from the center of the nucleus to the point where the density is maximum, right? And the measurement of this actual atomic radius is a very difficult task, and this is because the size of the atom is very small, approximately 1.2 angstroms, right? So why we cannot measure this atomic radius with actual values? We cannot have very defined values for this atomic radius, and the reason is one of the reasons which is suggested is that the size of an atom is very small, and however this size of an atom which is very small, the word size itself is not defined. What do you mean by the word size itself? Because the size of an atom is from the center of the nucleus to the point where the electron density is found, right? And this point is not well defined. Means, as from the quantum mechanics results, we know that there is no exact location for an electron. Rather, we have the probabilistic regions for an electron. So I mean to say that the electron's position cannot be precisely defined, and it is because of this result of quantum mechanics Bohr's model was also failed, because he has defined the path for an electron and it was exact path, right? So the problem is that we do not have well defined boundaries for an electron. So therefore the measurement for the size of an atom is not very good to understand, right? So precision cannot be accurate for that. So now we are going to estimate the radius, right? Estimation of radius means that we can have some just rough idea about the distance at which electron can be found, right? From the center of the nucleus to the distance where electron can be found. And remember that the atomic radius for any atom will never be the exact value. Rather, it will always be some approximate values, all right? So in order to measure, first we are going to understand the combined state of the two atoms, for which we will define the three types of the atomic radius. The covalent radius, metallic radius, have a look at the covalent radius. Now when atoms join together, right, to form molecules, like here in this animation we can see that the yellow atoms of these are a fluorine, then chlorine, and this purple one is bromine, iodine, sorry. Here is the bromine. Now when these combine, when they combine together to form molecules, we can find that there is a combination of two atoms, and then the distance between the two nucleus bonded two nucleus of the bonded atoms, right? That distance is called the bond length, right? And so now we can observe that very simply, that the atom fluorine have smaller size than chlorine, and the iodine is the largest one among all the four, right? And so here is the data that, for example, in case of chlorine, the distance between the two nucleus, right, is 198, and the half of that distance will give you this value 99 picometer, which can be regarded as the approximate size of the chlorine atom, right, from this nucleus up to the middle part, right? And similarly for iodine molecule, we can observe that the distance between the two nuclei is 266 picometers, right? And when you half that distance, means you half the bond length, this is called bond length, and when you half the bond length, we get the approximate value of the atomic radii, right? But keep in mind that there is a different situation, that these atoms are in bonded state, right? So there will be many different cases when iodine bonds to iodine, when iodine bonds to hydrogen, it bonds to sodium, and when this iodine bonds to any different atom, this size will change, right? So currently we have this value 133, and this value is called the covalent radius of the iodine. Okay, so that was about the covalent radius of the iodine. So how can we define this covalent radius? And this covalent radius, it can be defined as half of the internuclear separation between the nuclei of two singly bonded atoms, right? Singly bonded atoms, like when there is a single bond between the two singly bonded atoms of the same species, only then you can define it to be a covalent radius. That means the value of covalent radius will change when you change this partner atom. For example, when chlorine bonds to hydrogen, sodium, carbon and any other atom, then this 99 will definitely change, right? So here is the table from the NCERT book, table 3.6a and b, and here we can observe that in a period from lithium up to fluorine, we notice that the atomic radius is changing: 152, 111, 88, 77, 74 up to 64. And similarly for period number 3rd, from sodium to chlorine, we observe that the atomic size decreases. So the conclusion is that along the period the atomic size will decrease, and in table 3.6b we observe that in group 1 and in the second last group 17, we observe that as we move down the group, we observe that the atomic size increases. Similarly for group 17, the atomic size increases. Although it is required to mention that the increase in atomic size or decrease in the atomic size is not very regular, right? For example, you can observe that from 152 to 111, right, there is a decrease of more than 30 units, while from 88 to 77 there is a decrease of only 11 units. From 77 to 74 it is only hardly 3 units, and from 74 to 66, right? So from 66 to 64, so there is a different variation in atomic size, and we are not going to deal the atoms personally, but we are going to study them as group properties, right? So variation of atomic radii across the period, we can write down, we can note that in period the atomic radius decreases, but it is very important to note that the decrease is not regular in periods and as well as groups, right? Okay, this is the graphical representation, right? So we can observe that from lithium to sodium to potassium, rubidium and cesium, the size goes on increasing. And similarly for group number 17, fluorine, chlorine, bromine and iodine, again the atomic size increases. So we conclude that atomic size will definitely increase down the group and it will decrease along the period. But keep in mind that these observations are general observations, they are not always true. Okay, so that was all about the covalent radius. Now let us discuss the van der Waals radius. Now it is very important to understand what is van der Waals radius, right? First of all, we should note that the kind of bonding between the atoms, right? For example, you can see that there are two red balls, and this time these two red balls and the two green balls which you see here, these two green balls are the xenon atoms and these two red balls are the helium atoms. Now we can notice that because in case of noble gases, they do not combine to form diatomic molecules. Okay. So however, when we are going to liquefy them, solidify them, then these atoms of noble gases, they come very close to each other, but there is no sharing of electron, there is no electron common to both of these combined atoms, right? And these are also not called to be molecules, right? So keep in mind that the atoms, they have just approached towards each other, but there is no sharing of electrons, there is no covalent bonding between them. However, there is no covalent bonding, but the bonding which you observe, that this bonding is very weak bonding. Keep in mind that bonding is not related to always sharing of electron or gain or transfer of electron. It is related to the force of attraction, right? So these two atoms, they are bonded, right? But they are bonded with very weak forces of attraction, and these forces of attraction are known as the van der Waals forces. In later cases we will study it, right? So therefore the distance can be known as van der Waals bond length, and therefore the radius can be called as van der Waals radius. So it can be defined as the half of the distance of closest approach, right? It is closest approach, never say the bonded state. It is the closest approach between two non-bonded atoms of a given element. Now here is the very simple concept, that because if they were bonded covalently, then they have come closer to each other, much closer than this situation, and therefore the distance between the two nuclei must be very less in bonded state as compared to this state. So in that case we can understand that the covalent radius will always be smaller than the van der Waals radius. Alright. Now here is the comparison between them. We have bromine molecule and we have bromine molecule, and we observe that these two atoms in the bromine molecule, they are covalently bonded, right? But in liquid state, in solid state, we can understand that these molecules, they are not going to share another electron with these molecules. So they will remain at this much distance, and therefore these are not covalently bonded molecules, rather it is a covalently bonded atoms, right? So these molecules, they are bonded by the van der Waals forces, right? And therefore we can define it very clearly that if this is the covalent radius, this is the covalent bond length, and this half will be the covalent radius, and therefore this is the van der Waals bond length, and half of this, right, half of this means this much distance will be the van der Waals radius. So it is very simple to understand that the van der Waals radius will always larger than covalent radius. Okay. So now we will discuss the ionic radius. Now we have suppose cation and their atoms. For example, we have sodium atom. Now this bigger piece is called the sodium atom, shown in green. Alright. Now when sodium atom, it loses one electron to become a cation, then the size of the cation is always smaller than its parent atom. And we have to suggest the reason for this, right? So first of all, we mention the size. Here is the size 154 picometer from the center of the nucleus up to the valence electron cloud, and here is the distance from the nucleus to the valence electron cloud, and we observe that this size decreases, right, from 154 picometer to 116, it decreases. Now what is the reason for that decrease? As we know that the number of proton is 11 in sodium atom as well as cation, and we also know that the number of electrons in sodium atom is 11, but in cation it is now 10. So therefore we understand that the number of proton remaining same while the number of electron decreasing, this will increase the effective nuclear charge, and that effective nuclear charge will squeeze the electron cloud, and therefore it will reduce the cationic size. So therefore it is very important to understand that cations always have smaller size than their parent atoms. And what about anions, right? So in this case, as we know that increased effective nuclear charge in cation makes them smaller than the atom. And for anions, for example, suppose we have chlorine atom, and when this chlorine atom, it gains one electron to become a bigger chloride anion, right? And here is the size, we can mention it. It was 99 picometer before gaining the electron, and after gaining the electron it has become 167 picometer, right? And the reason is very simple. Because of decreased effective nuclear charge in anion, it makes them larger than atom. Moreover, whenever we understand that an electron is going to add into the valence shell, then their interelectronic repulsion will also increase. Therefore, we can understand this size should be larger than the atom, and this is the case. Okay. So now let us compare the cation and anion, right? Here is sodium cation, smaller in size than sodium atom. Here is chloride anion, larger in size than chlorine atom, and here is their size. This yellow middle line shows that to the left side of this is sodium boundary and to the right is the chloride boundary. Means this is the line where the positive field of sodium cation and the negative field of chloride anion neutralizes at this boundary. So this is the limit for sodium as well as for chloride ions, right? So we can represent the distance from these points as this one. So it is 116 and it is 167 picometer. So this will be called as sodium chloride formula. Okay. So similarly we can define the ionic radius. It is the radius of an atom's ion in ionic crystal structure. Okay. Here is the complete, not complete, it's a partial set of some of the cations and some of the anions. Those with red region, these are the cations, and those with the gray or blue region, these are the anions. And we can observe that very simply that in case of calcium, for example, the size is 174, and when it becomes cation the size becomes 114. Here is the sodium with size 154 when it is an atom, and when it becomes cation it is 116. Similarly for anions, for example chloride, we can observe that when it was an atom it was 99, and as it becomes an ion the size increases to 167. And second thing, we observe that down the group the size increases, whether it is an atom or an ion. And on this side we can observe that the size of atoms increases, size of cations also increases, size of cations also increases, right? But a very important thing to understand, now notice the periodic variation. First we are going to notice the atoms, just atoms part. Sodium 154, magnesium 130. Observe all the black numbers, right? Aluminium 118, sulfur 102, chlorine 99. And we observe that 154, 130, 118, 102, 99, the atomic size decreases along the period. Now observe the ionic situation. So for example sodium monocation is 116 and magnesium is now 86. Now I think you have noticed that the size of the atom for atomic size for sodium is larger than magnesium, but the ionic size of sodium ion is larger than magnesium ion, and it is much larger. Okay. And similarly we can observe that it has become 116, then 86 means decreased, then further decreased, and now increased. So what is the simple conclusion? Simple conclusion is that anions have always larger size than their parent atoms, and cations have always smaller size than their parent atoms. Alright. Now let us go for metallic radius. Here you can see the crystal of copper, a very crystal of copper. Each of them is just an atom, and this blur picture which you see is the electron cloud, right? So metallic radius is defined as 1/2 of the distance between the nuclei of the two atoms. In a crystal, right, between the two adjacent metal ions in the metallic lattice, right? And this can be shown easily from this. For example, this one is the one of the atom, then another atom, and the distance between the nuclei, the tip of this arrow represents the nucleus, and this tip also represents the nucleus. So this arrow represents the distance between the two nucleus, and half of this distance will be called as metallic radius for copper, right? And this case the distance is 256 picometer, and when you half that distance you get 128 picometer, which is the atomic radius of copper. We can call it metallic radius of copper, right? Now isoelectronic species. Now all those atoms, cations or anions, any species, any ion which have the same number of valence electrons, right, which is known as equal electric, right, or equal charge. So these are the species which are called the isoelectronic species. Means in simple statement we can say that this species, which can be an atom, an ion, right? Any species which have same number of valence electrons, right? This can be called as isoelectronic, right? So we can observe that for a period. Here is the species. This is called nitride, oxide, fluoride, neon, sodium, magnesium and aluminum. And you can observe the size 171, 145, 133, 154, then 98, 65 and 45, right? All the data is given in picometers. Now we observe that the size decreases, and you are not going to discuss this case, neon. Why? Because we know that neon is a noble gas, and in case of neon we have to measure the van der Waals radius, while in other cases we have the covalent radius or ionic radius, and van der Waals radius is always larger than the covalent metallic or ionic radius, right? So it is the largest radius. So therefore I have just written this to ensure that it is there in period, right? And from there it starts a third period. From sodium starts the third period. So therefore we are not going to discuss this neon case. So you can just imagine that this data is not available. Now the number of proton, if you observe that 7, 8, 9, 11, 12 and 13, that means number of proton are increasing, and the number of electron in this case is 10, because 7 electrons of nitrogen and the 3 additional electron when gained by the nitrogen, that makes 10. Similarly for fluorine there were 9 electrons, and when it gains 1 electron it becomes total 10 electron. For magnesium there were 12 electrons initially, and after losing 2 electrons it becomes total 10 electrons, right? So we observe that in case of isoelectronic species, when the number of proton increases, the atomic size increases, right? So now we can have a simple question based on this, right? And this is problem number 3.5 from your NCERT. Which of the following species will have the largest and the smallest size? Now take some time, think and then answer. Now first we are going to look at the largest. Now cations can never be largest, so we have to compare the magnesium and aluminium. Out of these two, since magnesium is lying to the left of the periodic table as compared to aluminium, so magnesium will have the largest size among these four, and smallest size will be of aluminium plus 3. Why? Because from magnesium to aluminium the size will decrease, and now it is 3 plus, so it will be further decreased, right? So this is the answer. All right.